Hi, I'm Sean Moran with ACCGIS, and our topic is data assimilation. And I want to kick the discussion off with a video by Lauren Bennett with ESRI, who's going to step us through how you can use data engineering to perform spatial data science.
Now, we've seen some amazing analysis already, but I want to zoom out a bit and take a look holistically at what spatial analysis and data science really encompasses. Now, each of these pieces are key components of doing great data science. But I think if we scaled them based on the amount of time that we take in each activity, it might look something a little bit more like this. Well, data engineering is arguably one of the most time-consuming parts of the analysis process. It's where we get our data ready for analysis. We do things like fill missing values or add new fields that we'll use in future analysis. And this part of the process is absolutely crucial because our analysis is only ever as good as the data that we put into it. With the upcoming release of ArcGIS Pro 2.8, we're introducing a brand new experience for doing data engineering inside of ArcGIS. It'll make exploring and visualizing your data easier and brings together tools from all across ArcGIS to construct, clean, format, and integrate your data to get it ready for analysis. And it probably sounds impossible, but I think we actually managed to make data engineering a little fun. So to give us a tour of this new capability, I'd like to introduce my colleague, Lakeisha Coleman.
Thank you, Lauren. Across the United States, many families are struggling to put food on their tables. Food insecurity, or the lack of access to food, has increasingly become an issue, especially this past year, and we'd like to explore the problem so that ultimately we can help inform policy decisions. In addition to relying on food banks, like those run by the Capital Area Food Bank, who created this powerful story map, many families also rely on public benefits like the Supplemental Nutrition Assistance Program, or SNAP benefits. For this research, I've pulled together data on SNAP benefits, as well as demographic and unemployment data, which we tend to include in this type of analysis. But, like most data, this data is messy and not analysis ready. A common starting point is just cracking it open and looking at the table, which takes a lot of manual work to explore each field, to get a better sense of the data. The new data engineering experience makes this really easy. It brings together lots of capabilities in one place, helping you to move from the often tedious data engineering process and into your analysis quickly. You can see the different data types, visually explore the data, looking not just at the raw data, but mapping each variable with a single click to learn more about its spatial patterns, such as median household income or perhaps average household size, as more people in a household changes benefits received. I can also add these fields into my summary statistics view and start to learn a lot more about my data. I get a powerful overview of my data, such as histogram charts showing the variable's distribution, summary statistics such as mean, standard deviations, and outliers, as well as this column for the number of nulls or missing values. First, I want to see where those missing values are on my map. If they were all clustered together, for instance, this might indicate an issue with data collection. This is a great example of information that is critical to my data engineering and only possible when I think about the problem spatially. In this case, they look pretty random, and I'm comfortable using the Fill Missing Values tool so that these don't present an issue later in my analysis. With the simple right click, I bring up the tool and choose to fill in missing values using spatial neighbors, a really powerful way to take advantage of using spatial relationships, and I run my analysis. When I run this, those results can be found within the attribute table with those previously missing values now filled in. Back in the data engineering view, I remember seeing a skewed distribution for the participants that I'd like to deal with. With a right click, I choose Transform Field, and I'll input the necessary information. This skewed distribution was expected, as this is a count measurement and counts tend to be skewed. Once I run this back in the data engineering view, I'll recalculate. And the results go from that skewed distribution to a more normal distribution, such as this, which is much better for the analysis. There's also this data engineering ribbon, which gets activated with the view. Within the ribbon, you'll find more data engineering tools to make your process as efficient as possible. Tools for clean, such as delete fields or find spatial outliers. Construct, if I need to calculate or add a field. Integrate for those analysis tools to do those fundamental GIS operations such as enrich. And format, I can convert a time field or encode a categorical variable. So many useful tools all within this ribbon. In this case, I'll go back to construct, and I'm interested in performing dimension reduction, a common data science technique. I have a lot of population variables, and here I'll use a principal component analysis to condense my data into a few components which I can use again in future modeling. These components will then be added to my data set so I can explore them further and use them in my analysis. And lastly, this past year has shown us the importance of being able to pull the latest data quickly, automate it, and also repeat the process. I can simplify this by creating a notebook where I can capture all the details of my process, why they're important, capture code, capture commands, and share with colleagues if needed. Now I'm ready to continue my work in researching food insecurity in the United States with the help of these great data engineering capabilities. Thank you.
By the end of this topic, you'll be able to explain how ETL, or extract transform load, is used to assimilate data. You'll be able to describe how vector, raster, and triangulated data are modeled in GIS. You'll be able to create geodatabase subtypes and attribute domains in GIS. And last, you'll use ETL tools to assimilate data in GIS. Let's begin our data assimilation discussion by focusing on the ETL process to import, convert, and write data from a source to a target format. Now, ETL integrates data from one or more sources in 3 steps: extract, transform, and load, where we extract data from a source database, we transform the source format to a target format, and we load the data into a target database. If you look at the image in the lower right-hand corner, you can see where we're visualizing this process where we're extracting from multiple files or data sets, transforming it, and then loading it into our target database. Now, there are different approaches for extract, transform, and load. One is manual or automated. Manual, or what I like to refer to as brute force, is when you're taking the data from one format and then you're kind of manually converting it to your target format. Now, I do this a lot if I'm doing like one-offs or I just need to do something really quick, and it's much easier just to do it manually. But if I find myself having to transform large amounts of data or on a regular basis, then I might want to turn to automated ETL, where I'm utilizing geoprocesses or scheduling software or even Python scripting languages to automate the ETL process. Another difference in approach is ETL versus ELT. So ETL stands for extract, transform, load. ELT stands for extract, load, transform. And why would you want to switch those last 2 steps? Well, most commonly, we're extracting the source data, transforming it, and loading it into our target format. But sometimes we're more comfortable in our target format and software. And so instead of the ETL process, we'll flip it around. We'll extract the data, go ahead and load it into our target format and software, and then we'll transform it in that software. The last approach I want to discuss is the difference between ETL versus federated. ETL is where I'm trying to consolidate all my data into my target format. And if I have, for example, a unique project that I'm working with, I might want to do that, taking all my data and consolidating it into a single geodatabase. But if I work for an organization where I have standalone databases that are very large and or changing frequently, I might want to use a federated process where instead of transforming all the data all the time into a target format, that I maintain a metadatabase that has connections to these standalone databases that I can utilize to query, analyze, and visualize the data on demand. So the benefits of the ETL process include converting data, the ability to integrate data from multiple sources, and also the ability to automate the ETL process. Now let's take a closer look at each step in the ETL process. In the extract stage, we're importing and validating source data. So importing data into a staging area, including a file or files, or a database or databases, or even an application, for example, Twitter or Facebook. But the extract process isn't just about importing the data, it's also about validating the source data. So there are a number of validation processes that we can run when we extract our data, including reconciling the records with the source data to make sure that the count of records, for example, in the source data are the same as the count of records that have been extracted. To ensure spam or unwanted data is not loaded, there might be characters or information that we don't want. We want to make sure we exclude that. To verify data types, for example, numeric or text data types. To remove duplicated or fragmented data. And last, to confirm that keys are present, for example, primary keys and foreign keys, so that we can create our necessary relationships once the data is loaded into our database. The second step in the ETL process is to transform, where we clean, map, and convert data. Cleaning data might involve, for example, standardizing character sets, values, or null values. Maybe you have blank values, or you have values that have leading zeros, for example, and you want to standardize that as you're transforming the data in. You also might translate coded values and encoded freeform values. So converting coded values like 1, 2, and 3 to low, medium, and high, or maybe the other way around, low, medium, and high to 1, 2, and 3. We can also concatenate, parse, or calculate values, so combine values, divide up values, or create new values. We can sort or order data to improve performance. We can even normalize and/or relate data in the transformation process. The transformation process also involves mapping the data, which means selecting which fields you're going to load and then mapping those source fields to the destination fields. So you might not want all of the attributes for the source data, and you can exclude some of the attributes. And then for the attributes that you do include, you want to make sure that you map each field in the source to each field in the destination, so the source data gets properly loaded into the target data. The last part of the transformation process is to convert the data, and that is to transform from the source format to the target format. The last step of the ETL process is load, where we write validated data into a target database. And there are different types of loads. There's initial load, incremental load, and full refresh. An initial load is where we're just loading all new data. You can imagine if Austin Community College started a new process where we needed to communicate with all of our students, for example, we might do an initial load where we take all 70,000 students and load them into the database. An incremental load is where we append new or update change data. And so in the previous example, maybe it's the next semester. And so rather than loading all 70,000 students again, I only need to load any new or changed student data. The last type of load is a full refresh, and that's where you're replacing all the existing data. Sometimes the data gets out of sync and you just want to go ahead and flush it all out and do a full refresh. And you can use the load process to do that. In addition to loading the data, you also validate the data during this step, and that is ensure, for example, the primary and foreign keys are populated correctly so it supports any relationships that you want to create, to confirm that all the values transformed correctly, and then last, to compare the stage data to the loaded data to make sure that all the data made it across. As GIS professionals, we're often not just tasked with extract, transforming, and loading attribute data, but spatial data as well. And this is known as spatial ETL, where we're importing, converting, and writing spatial data from a source to a target format. And so it includes all of the ETL functionality for attribute data plus spatial data. Some of the spatial transformation functions include transforming from one coordinate system to another, creating topological relationships to better understand connectivity between features, resymbolizing layers, geocoding location data. In the previous example where I talked about importing all of the students at ACC into a database, if you had their address, you could actually geocode their addresses to add their XY locations to the database. You can validate, repair, and convert geometry. You can even perform some basic and advanced geoprocessing. And just so you're up to speed on the lingo, sometimes spatial extract, transform, and load, or spatial ETL, is known as geospatial transformation and load.